Hello and welcome to the episode 9 of PyTorch Code Deep Dive. In the last episodes I showed how module is internally designed, and in this episode I will show how state of the module is managed. If you find presented content useful, don't forget to press the like button and subscribe. Module state captures content of the module during and after training. I'll be using example from the previous episode with custom parameter and buffer. I will print state dig result. This method outputs dictionary filled with tensors. Let's see what is inside. This method allows specifying object to put results into. If it's not declared, new ordered dictionary is created. PyTorch stores additional metadata information with version number. The version is stored for top level. State dig hooks are triggered if any were registered to signal that state is about to be generated. Then internal save to state dig is called with empty prefix for top level. This method iterates over all parameters and adds them to the destination dictionary. The key is composed from prefix and parameter's name. By default, keep vars is false, so tensor that backs parameter is detached. Same happens with buffers, but only for persistent ones. If module overrides get extra state, the result is also stored under special extra state key. This can be used to attach extra information when implementing module. After handling module's direct parameters and buffers, each submodule is called recursively and state is captured in already created dictionary. Prefix is expanded with the name under which the submodule is stored in module's dictionary. Here's the example for sequential submodule. Once recursive call returns, we see that sequential submodule added information about multiple linear layers. As a last step, another type of hooks are called, and content of the final destination dictionary can be modified for this module. Let's capture this state and load it back to the module by passing it as a parameter. We see that it's expected the state dictionary to be a mapping. This method will check the content keys of the dictionary and if these match module structure. Since input state dictionary may need to be modified, the content is copied into ordered dictionary. Metadata is explicitly attached to the dictionary with each submodule's versions. The internal load function will handle the rest, and for this module, private load from the state dig is called. At this point, yet another hooks are called to notify about incoming state loading. The next lines capture all persistent buffers of this object and all name value pairs of parameters and these buffers. Local state will keep all values which are not none. Next, we iterate over these state objects. The name reflects module structure, as prefix was given as a function argument. If the corresponding parameter is present, in the incoming state dictionary it's retrieved to local variable. There are additional backward compatibility checks that I will skip for now. By default, swap tensors and assign to params buffers are disabled. Therefore, by default value from input dictionary is copied into module's parameter. This is repeated for all modules parameters. If strict is true, which is the default, and some parameter is missing in the input, the key is recorded for later introspection. If extra state is present, it's applied directly at this very moment. As a last step, there's an additional check for strict loading for additional values in input dictionary. Any such values are reported in unexpected key structure. As there were no modification to past input, we don't expect any surprises. The second step is to call load function recursively for each submodule. In this case, only subset of state dict is passed and the range of data is indicated by the prefix and submodule's name. Flattened module has no parameters, so I will skip it. There's a range of values for sequential module though. It's important to pass only state related to specific module, otherwise it would trigger false elements into unexpected and missing keys. As a last step, hooks are notified that loading is done. On strict loading, any presence of either unexpected or missing keys will trigger detailed error message generation and will raise error that fails loading. Otherwise, these keys are returned to the caller for further introspection. In this video, I showed how internal state of PyTorch module is managed. In the next video, I will show how name attributes can be managed in PyTorch module. If you like this video, make sure to press like button and subscribe. I hope my content will help you creating something great. Thanks for watching.